A while ago, I ordered myself this so-called Launchpad, which in my opinion not only features a rather decent build quality for only €70, but also offers a total of 64 square push buttons and 16 round push buttons. By connecting it to a computer through its micro USB port, the push buttons can for one light up, but can also be used with music software, like for example FL Studio, to play back certain tones. This way you can, if you're talented enough, create music, which does not sound that nice in my case, because hey, I'm an engineer and not a musician. But just search for Launchpad on YouTube to see what kinds of amazing things you can do with it. Anyway, while playing around with the Launchpads, I was starting to wonder how exactly the push button matrix works, and what kind of data it sends over to the computer. So in this episode of DIY or Buy, I will not only show you how I mechanically and electrically built my own Launchpad in order to find out whether DIYing such a device is worth it, but I will also talk a bit about the keyboard matrix and MIDI, aka Musical Instrument Digital Interface. Let's get started. This video is sponsored by JLC PCB, where you can get 10 PCBs for only $2, with 24 hours express turnaround. Their focus is high quality PCBs for a low price, which you can get delivered within a week. The first thing to figure out when it comes to recreating such a complex electrical device is a plan. Since I wanted to keep things simple, I kicked out the round push buttons from my design and reduced the number of square push buttons from 8x8 to 6x6. For the outer shell, I wanted to use regular PLA filament, but a semi-flexible filament called Polyflex for the buttons, since it is more comfortable to push and also more translucent for the LED lights. And speaking of LEDs, I will be using WS2812 LEDs, since they only require one data pin besides 5 volts and ground, in order to control all 36 mandatory ones, which saves us a few I/O pins of the Arduino Nano microcontroller. Most of the other Arduino pins will be connected to the keyboard matrix, which I will talk about in detail later. For now, all I needed to know about the matrix was that I will be using those rather big tactile switches, which come with a little plastic head. Here began the most complicated part though, since we had to precisely measure all the components and create a mechanical blueprint. There will be 2 perf boards on the bottom that are mounted to the enclosures inside with screws. On those perf boards are all 36 tactile switches soldered onto, whose heads are close to the upper 3D printed bottom mats. 3D printed prisms will be positioned between the tactile switch rows, onto which the LEDs will be mounted to illuminate each button at an angle. Sounds complicated at first, but while looking back, this design idea worked out pretty well. Now with the blueprint in mind, my assistant created a 3D model with 123D design for the main enclosure, the lids, the 6 prisms and the push button mats. So I started off by 3D printing the semi-flexible mats, whose first attempt was a big failure, since the extrusion speed was too high. But after decreasing it to 39% for the second try, the print turned out successful, but was certainly not easy to remove from the build platform. All the remaining prints required less attention from me during printing, since they were created with easy to handle PLA Prucement, whose quality was pretty awesome to look at after I removed all the support material. But anyway, after cleaning up the mat as well, it was assembly time, which I started off by inserting the mats into the main enclosure. Next, I pushed all 6 prisms into their cavities inside the enclosure, and moved on by cutting 36 individual WS2812 LEDs from a long strip, which I obviously tested beforehand. Then I marked the start LED and the direction of the LED's data on each prism, which resembles a snake pattern. Afterwards, I removed the prisms and used superglue to mount each LED with the correct orientation in their designated space, indicated by the bigger width of the prism. As soon as all 36 LEDs were secured, I pre-tinned their solder pads and used silvered copper wire to connect the pads of the neighboring LEDs. Once that was done, I positioned the prisms inside the enclosure once again in order to determine the length of the connection wire between them, which I then cut into the appropriate length. Needless to say, I then used this thin 0.75mm flexible wire to connect the ground, 5V and data pads of the neighboring LED prisms. Next, I brought in the two perf boards, which feature dimensions of 10 by 20 centimeters. According to the size of the enclosure, I scored them and snapped a piece of them off in the horizontal and vertical axis so that they fit perfectly inside the housing. Afterwards, I reinserted the prisms and did a bit of cable management before I used superglue to permanently secure them in their cavities. Through the help of the perf boards and a bit of ballast, I let the glue dry and afterwards tested whether the LEDs still functioned correctly, which they did. At this point, I positioned the tactile switches in one half of the button map, laid a perf board on top and marked the position of the switches. I then pushed all the switches into the marked spots, added their plastic heads and positioned them in the enclosure once again with a bit of force. And as you can see, these switches seem to work correctly, so I repeated pretty much the same procedure for the other half of the launch pads. As soon as I was sure that all switches worked correctly, I permanently soldered them in place and connected one side of all the switches in one column together with silvered copper wire. But wait, why am I doing this? Well, let's say we got 36 switches. To check which one gets pushed, we could connect one side of each switch to a digital input pin with a pull-up resistor, and all the other switch sides to grounds. If the switch is not pushed, we get 5V on the digital pin, and if it is pushed, we get 0V. Easy. Only problem is that we would need 36 digital inputs for that, which we do not have. The solution is to connect one side of the switch in all columns together and the other side of the switch in all rows together. Now we can connect each column to an input with pull-up resistor and each row to another pin, which means we only need 12 pins. The procedure is simple as well. We look at one column and pull each row down to grounds, one after the other. If at one row the input at the column gets pulled down to grounds, we know that this switch is activated. After checking all rows, we then move on to the next column and repeat this process. And since we go through the scanning process so fast, we can pretty much capture any human button press. I later also added diodes to the ground side of the switches to prevent ghosting. But feel free to read the Keyboard Matrix help article from Dave Dribbin to get more information about that. Anyway, like I just described, I created all 6 column lines and then moved on to adding a diode to the other side of each tactile switch. Once that was done, I reinserted the perf boards and created M5 and M4 threads for the enclosure's mounting screws. Before I marked the mounting holes for the perf boards, which I then created as well as a feed-through hole for the LED wires. Afterwards, I created a few more cutouts in the perf boards in order to properly secure them inside the enclosure with M3 and M4 bolts. At this point, I once again used silver copper wire to create all the row connections and finally used a bit of 0.75mm flexible wire to connect the matrix columns and rows and the LED wires to the Arduino according to this scheme. After then mounting the Arduino with a bit of glue, I closed the launchpad up with its lids and M5 screws, which means it was time for programming. To keep things simple, I utilized the keypad library, as well as the fast LED library. In the codes, I simply defined which pins are connected to the rows and columns, and then used a switch statement to light up each LED according to its fitting button press. After uploading the codes, you can see that the launchpad lights up just like I intended it to do. But how can we connect it to our music software? Well, the software can only interact with MIDI controllers, which coincidentally our commercial launchpad is. The sent musical instrument digital interface data consists of 3 bytes. The first one states whether a note is on or off and which channel we use. With 10010000, we say that the note is on and we use the channel 0. The next byte defines which note number we want to play, which can be 0 to 127. The last byte then defines the note velocity, which once again can be 0 to 127. You can also easily find a chart with all available MIDI commands on the internet if you're interested. Anyway, for my codes I added 3 serial write commands to each button push for the 3 bytes, and basically only changed the note value for each button. But after uploading the codes, the software did not recognize our MIDI device yet. For that, we firstly need to install the Loop MIDI software in order to create a proper MIDI port. And afterwards, we need to start the Serial MIDI Bridge software and start our data communication, which, as you can see, seems to receive proper MIDI messages if we push a button. And just like that, we can select the Loop MIDI port in the FL Studio software, map each button of our DIY launchpad to an instrument, and use it just like a proper launchpad. Now of course, it does not feature as much buttons, and took a lot of work to create. But I like the fact that I can use it easily for other electronics projects as a controller. That is why I declare that both DIY and buy are this time the winner. But what do you think? Let me know your thoughts in the comment section below. As always, thanks for watching, stay creative, and I will see you next time!